So today we're looking at 8.2, products and quotients of functions. Now, before we get into the lesson for today, I want to go over just some basic properties of multiplying and dividing. We're going to use these properties to help us come up with graphs of functions. Okay, so what's a property of multiplying that we know? We always are going to know. We know that a positive number times a positive number is going to give us a positive. Okay, so something positive times something that's positive is going to give us a positive. Okay, what's another property that we're going to know? That a negative number times a negative number is positive, and that a negative times a positive is going to give us a negative. And we know that those three rules are going to work for division as well. Okay, so a positive divided by a positive is going to give us a positive. What's another property of multiplying that we know? Okay, so any number times 1 is that number. That's true. We're not going to use that one a whole lot today, but that one is true. One we will use today is that any number times 0 is 0. Okay. We know that any number times something that's very small is going to get really close to 0. Okay. And so by really small, I'm looking at, or I'm talking about an exponential as it gets really close to 0, but never actually getting to 0. We're talking about as we're approaching asymptote. So what happens is it approaches 0 from the left or 0 from the right, something like that. We know that a number times something that's really big is going to get towards infinity. Okay. So if we have like the top part of an exponential, those numbers are getting close to infinity. So if we multiply something by that, it's going to be heading out that way as well. Similarly, if we take a number and divide by something really small, what's our answer going to be? If we're dividing by something that's really, really close to 0, it's getting really close to infinity. And if we take a number and divide it by a really big number, what are we going to get? We're going to get something that's getting really close to 0. Okay. Our first example, let's define our function f of x to be x plus 2. And let's define our function g of x to be x squared plus 5x, sorry, minus 5x minus 14. Okay, so we have two separate equations, and we're going to find those and look at the combination of functions. So the first way we're going to look at that is for a, let's define h of x to be f of x times g of x. So we look at this, we've defined h to be our function f times our function g. Well, let's look at this and say, all right, well, we know that f is x plus 2 times g, which is x squared minus 5x minus 14. Okay. We could multiply this out. So there's two things we could do. If we multiply it out, we can head over here and we will get that h of x is x cubed minus 3x squared minus 24x minus 28. Okay? If we take these and multiply out this brackets, collect like terms, we can get this expression for our function. What do we know about our function h at this point? Okay, it's a cube, so it's a degree 3. What's the leading coefficient? Is it positive or negative? Okay, so positive leading coefficient. Combine those two facts? What are they going to tell us? What do we know about our function? Okay, so we know a cubic, it's going to look like that. So quadrant 3 to quadrant 1. 1, 2, 3, 4. What else do we know about that function? So we use here, we have a point 0, negative 28. So we take that expression, one way we expanded it out, we got that it has degree 3, it has a positive leading coefficient, so it's going from 3 to 1. We also looked at the end term, and it told us that we have a y-intercept of 0, negative 28. We could also take that and factor it. Can't really factor the first term, but if we look closely at the second term, we can factor a quadratic that's x squared minus 5x minus 14. That'll go to x plus 2, x minus 7. So we have x plus 2 from our first term, x plus 2 from our second, and then x minus 7 from our second. Because those x plus 2's are the same, we can write those as x plus 2 squared x minus 7. So a different way to write our function h. Writing it this way, what does it tell us? Ben? We have zeros. Where are zeros? Negative 2 and positive 7. What about the 0 at negative 2? Because of this squared, it's order 2, which means it's going to cross our 0 like it's going to act like a quadratic around that 0. So now we can pull all that together, and we can get a graph for our function. We have zeros at negative 2 and positive 7. We know our end behavior, that it has to start in negative 3, or start in quadrant 3, finish in quadrant 1. We have a 0 at negative 28, so we can put that right there. It acts like a quadratic around negative 2, so it's either going to go like that or like that. And the only way for it to work is if it starts here, goes like that, and out. So that's a graph of the function f times g. Okay, so for our second example, we're going to look at the function. We're going to find f to be 2 to the power x, so an exponential. We're going to define g to be sine x. So if we look at those, just kind of get a sketch for them, we know that our exponential is going to have this shape. Okay, it's going to cross here at 1. We have numbers that are very close to 0 on our left. We have numbers that are getting very big on our right. If we look at our sine curve, it's going to repeat like that. Okay. going both to the positive and negative. We know that's going to have a max at +1, a min at -1, and we're going to have zeros at pi, 2 pi, negative pi, negative 2 pi. Okay, so we're going to use this graph, the kind of the properties from it, the properties that we talked about at the start of the lesson, to get a graph for these functions. The first function, let's define h of x to be f times g, which is going to be 2 to the power x times sine x. So starting at trying to find out what a graph of this is going to look like, the first thing we're going to do is look at our properties, and this one's going to come in very handy, that any number times 0 is going to be 0. So if we go over to this, we know that sine x has zeros at -2 pi, -pi, 0, pi, 2 pi, and so on. That means our function h of x is going to have zeros at those exact same spots. So if we're looking at starting our graph, our function h, maybe I'll put it in green, is going to have zeros at 0, at pi, at 2 pi, and so on, and it's going to have zeros at -pi and -2 pi. So now we've looked at our function and we figured out where our zeros are. Those zeros have to be there. Okay. What other so now we're looking at what's going to happen in between the zeros, because we know they're either going to be above our x-axis or below our x-axis. We need to figure out where it's going to be. So what's going to be happening in this interval here between 0 and pi? Okay. To do that, to figure that out, we look at the signs of those two curves. In this interval, sine is positive and our exponential is positive. So we're going to have a positive number times a positive number. So our result is going to be positive. And it's going to look something like that. Because it starts at a 0, ends at a 0, it has to go up and come back down. In the second interval, between pi and 2 pi, we have a positive number from our 2x times a negative number. Okay? And what's happening in that is that this 2 to the power x function is getting bigger. So you're multiplying a bigger number by something that's negative, so our graph is going to start coming down a little bit farther. Okay. And what's going to happen is that because our 2 to the x keeps growing and our sine curve keeps having these regular intervals, the size of our jump from our x-axis is going to keep getting bigger the farther we go out. Going the other way, we're still going to have these regular zeros. Now we have a positive number times a negative number. It's going to be negative, but now our 2 to the power x is getting really small. And the further we go out to the left, that number keeps getting closer to 0, so the size of our waves keeps getting smaller and smaller. And that's going to be a graph of our function 2 to the x times sine x. So the second one we'll look at doing is we'll look at a division one. So we'll go, let's define k of x to be f of x divided by g of x, which is going to be 2 to the power x divided by sine x. Okay. So if we're looking at getting a graph of this one, 2 to the power x divided by sine x, what do we have to, or what do we know on off the start? What's going to give us trouble with this one? Well, this one, because sine is in the denominator, it's possible for our denominator to equal 0 in this case. Can we have a denominator equal 0? No, so what's that going to give us? We're going to get vertical asymptotes. Vertical asymptotes at sine x equal to 0. Okay. So if we start with our axes, we know that sine is 0 at 0, pi, 2 pi, negative pi, negative 2 pi. So those are going to correspond to asymptotes. So in our first section, both of them are positive. We're going to be dividing by a negative number, which makes things go towards infinity. So those are all positive numbers, so this one's going to be going up. In our second section, our 2 to the x is still positive. Our sine x is going to be negative. So if we're dividing by a negative, it's going to go to negative infinity. So it's going to be opening down. And because the sine curve, 2 to the power x is getting bigger, this one's just going to open down from farther from the x-axis. Okay. And we're going to get the same thing going here, but the farther it goes to the left, the closer it gets to the x-axis. And that's just because of 2 to the power x getting smaller. Okay, so the last one we're going to do is we'll define L as g over f, which is sine x over 2 to the power x. Okay. Now, looking at this one, do we have any concerns with our denominator? Is there going to be any problems there? Why or why not? Well, it's not only that can it not be negative, it's always going to be positive. So 2 to the power x is always greater than 0, which just means there's no asymptotes. Okay, our denominator can never be 0. It's going to get very close to 0, but it's never actually going to be 0, so we don't have to worry about any asymptotes there. So if we're starting our graph, where are our zeros? So our zeros are when sine x equals 0. So again, at 0, pi, 2 pi, both positive and negative. Okay. So we know that 2 to the power x is always going to be positive. What else do we know about 2 to the power x in terms of the size of the number as it moves from left to right? Well, 2 to the power x is going to be small on the left side and bigger over here. Okay? So when we're dividing by a big number, it's going to make the resultant really small. And we divide by a small number, it's going to make the resultant really big. Okay? And we know that for a sine curve, positive, negative, positive. So in this interval, our sine curve is positive. In this one, it's negative. This one, it's positive, and it'll alternate all the way across. Okay. And because it's getting divided by a number that gets bigger as we move to the right, the size of the the wave is going to get smaller as we move to the right. And because it's getting divided by a smaller number to the left, the size of the wave is going to get bigger as we head out this way. Okay. And the pattern would keep going, keep growing as it goes to the left, and keep shrinking down as it goes to the right. Okay. And that's how we can get an approximation of the graph for the combination of functions.